Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Interview questions and answers in chemical engineering. Chemical Reaction Engineering Part 1. I would appreciate you if you subscribe to the channel, which is striving hard to deliver valuable knowledge content for your career progress. So subscribe now before you forget. For every question, you are given 20 seconds to think about your answer. Then the answer will appear. Check your answer is correct. Wherever required, detailed explanation is given. Chemical Reaction Engineering Part 1 consists of 5 questions. Question number 1. It consists of 2 parts. Part A. Explain what is the role of catalyst in a chemical reaction. Part B. What factors influence the rate of a catalytic reaction compared to the uncatalyzed reaction of the same reactants? Your time starts now. Your time is up. The answer. A catalyst is a substance which provides an alternative route of reaction where the activation energy is lower without actually taking part in the reaction. This figure illustrates the role of catalyst in a chemical reaction. As illustrated in the figure, the catalyst reduces the energy required to reach the transition state of the reaction, allowing more molecular interaction to achieve their state. Observe the reduced energy due to use of catalyst, equivalent to delta EA. Catalysts do not affect the chemical equilibrium associated with the reaction. They merely change or increase the rate of reactions. The amount of catalyst do not change during the reaction because it does not take part in the reaction. Rate of a chemical reaction is influenced by the temperature and the composition of the components in the reactor. The reaction rate with respect to the reactant A is given by the expression minus RA equal to K into concentration of ACA to the power m, where m is the order of the reaction. The expression for the reactant constant K is K0 into e to the power minus E by RT, where K0 is Arrhenius coefficient and E is the activation energy. Hence, the rate of reaction is a function of the energy level, which is the temperature, and the concentration of the materials. From the rate equation, you can notice the term activation energy E. As the activation energy increases, the reaction rate decreases. Certain reactions need large activation energy or very high temperature to begin the reaction or proceed at an appreciable rate. The catalyst reduces the activation energy required for such reactions and break the barrier that exists to initiate the reaction at lower energy level or temperature. Consider the uncatalyzed reaction with activation energy EA. For a catalyzed reaction, the activation energy is reduced by an amount equivalent to delta EA. The rate constant KUC for an uncatalyzed reaction is expressed as KUC proportional to exponential minus EA by RT. The rate constant Kc for a catalyzed reaction is expressed as Kc proportional to exponential minus EA minus delta EA divided by RT. The ratio of the rate of catalyzed reaction to the uncatalyzed reaction is expressed as Kc divided by Kuc becomes exponential minus EA minus delta EA by RT divided by exponential minus EA by RT, which is equal to exponential delta EA by RT. Thus, a catalyst increases the reaction rate by a factor of exponential delta EA by RT. Question number 2. In a plug flow reactor, the following irreversible addition reactions are taking place in parallel. A plus B giving rise to C plus D. A plus B leading to formation of E plus D. Product C is a desired product. If you have to maximize the formation of product C, what reaction related data you will analyze and what actions you will take. Your time starts now. Your time is up. The answer. Though C is the main product you want to produce, reactions to form E is also competing for the same reactants A and B. Hence, it is necessary to optimize the reactor operation such that formation of product C is maximized. Two ways to control reactions for favorable product distribution are: 1. Increase the reaction rate for desired reaction compared to the side reactions. 2. Study the activation energy of the reactions and fix the reaction temperature accordingly. If the reaction pathway 1 is a desired one, then the ratios K1 by K2 should be adjusted in favor of K1, where K1 and K2 are the reaction rate constant for reaction 1 and reaction 2 respectively. The activation energy of the competing reactions E1 and E2 respectively should be studied. If E1 is greater than E2, the reaction temperature of reaction pathway 1 should be maximized. On the other hand, if E1 is less than E2, the reaction temperature of the reaction pathway 1 should be kept low. This will lead to favoring the formation of desired product C through reaction pathway 1. Question number 3. What is zero order reaction? Give one example of zero order reaction. Your time starts now. Your time is up. The answer. Zero order reaction is a reaction that has a rate that is independent of the concentration of the reactants. The rate expression for a zero order reaction for reactant A is written as minus RA equals K times Ca to the power naught, which simplifies to minus RA equals to K. The rate of reaction minus RA has units of moles per unit volume per unit time, that is concentration per unit time. Hence, the rate constant has units of concentration per unit time. Applying the units of reaction rate and rearranging the rate equation in terms of unit, we get moles per meter cube equals rate constant into time. A plot of concentration versus time can be made as shown in this figure. So the K is a negative slope of the line obtained. So in a zero order reaction, increase or decrease of concentrations of the reactants will not increase or decrease the rate of reaction. Zero order reactions are usually found when a material that is required for the reaction to proceed, such as catalyst, is saturated by the reactants. An example of zero order reaction is the cracking of ammonia, which is a reverse Haber process under the influence of catalysts such as platinum at high temperature in accordance with the following reaction. 2 moles of ammonia getting cracked into 1 mole of nitrogen and 3 moles of hydrogen in a gas phase reaction. The surface of the catalyst is fully covered with gaseous ammonia, and the change of pressure or concentration will not change the adsorption of the gas on the surface. Another example of the zero order reaction is the formation of hydrogen chloride from hydrogen and chlorine in accordance with the reaction shown below. Question number 4. What are the different types of reactors you usually find in the chemical process industry? Explain with graph in which type of reactor the conversion is time dependent and in which reactor the conversion is position dependent. Your time starts now. Your time is up. The answer. The types of reactors commonly used in the process industry fall into two main categories. 1. Batch reactors. 2. Continuous flow reactors. This figure illustrates a batch reactor. The reactants are initially added to the reactor vessel and are well mixed. The reaction is allowed to proceed for a certain period of time. After that, the contents are discharged. This is an unsteady state operation, meaning that the concentration changes with time. But at any point of time, the concentration inside the reactor is uniform. In a batch reactor, there is no input, there is no output when the reaction is occurring. Continuous agitation is made till the reaction is completed. Continuous flow reactors can be categorized into two main types. 1. Continuous stirred tank reactors CSTR. 2. Plug flow reactor PFR. The CSTR is also called back-mix reactor or mixed flow reactor MFR. This figure illustrates a continuous stirred tank reactor CSTR. The feed is continuously added to the reactor and the reaction rate is controlled with the addition of the reactants, and the contents are well stirred and uniform throughout. The product leaving the reactor has the same concentration as the product within the reactor. CSTR is operated at steady state, meaning accumulation is zero and assumed to be perfectly mixed. This makes the temperature, concentration and reaction rate independent of position in the reactor. This figure illustrates a plug flow reactor, the second type of continuous flow reactors. It is an unmixed reactor and the flow is orderly with each element or slug of fluid not overtaking or mixing with another element or slug ahead or behind. In PFR, the key assumption is the fluid is perfectly mixed in the radial direction. Each plug of differential volume is considered as a separate entity. As the plug flows through the PFR, the residence time of the plug is a function of its position in the reactor. Plug flow reactor is operated in a steady state. As illustrated in this figure shown, in a batch reactor, the conversion is a function of time. The number of moles of reactant A decreases with time, and the number of moles of product B increases with time. For a plug flow reactor, the conversion is a function of its position or length or volume. That is to say, the conversion increases with the length or volume of the reactor. This figure illustrates the change of concentration of reactant and the product with the reactor length or volume in a plug flow reactor. Question number 5. A chemical process has its equilibrium conversion limited by thermodynamics. For such a process, how will you improve the conversion to 100%? Explain the system with a real-world example. The time starts now. Your time is up. The answer. In several chemical processes, in petrochemical plants, process plants, and fertilizer plants, the extent of chemical reaction or conversion is limited by the chemical equilibrium. Examples of such thermodynamically limited processes include propane dehydrogenation, ammonia synthesis, and methanol production. In these examples, the reactor conversion is limited by equilibrium concentration at the design operating conditions of pressure and temperature. Usually, the pressure and temperature conditions which favor the conversions are selected and conversion is optimized. But in the real world reactors, there are limitations to increase the temperature and pressure due to practical considerations. So in most cases, the conversion is below 50%. The usual accepted concept of increasing the conversion is to recycle the unreacted reactant material to the reactor. It is not easy. The reactor effluent has products of reactions also. The unreacted feed material needs to be separated to produce products that meet the product specification, and then the unreacted material is recycled to the reactor. Thus, the feed to chemical reactor is always a combined feed consisting of 1. Fresh feed, 2. One or more recycled streams, mostly the unreacted excess reactant. So what is the type of system you need? You need a reactor, separator, a recycle loop. In the ammonia synthesis, the equilibrium conversion is limited to less than 50% at temperatures and pressures of 350 to 400 degrees centigrade and 200 bar respectively. In this reaction, there is a reduction in number of moles as the reaction proceeds from 4 to 2. Hence, reactor conversion can be increased by increasing the pressure, but practical considerations limit the operating pressure. However, with the recovery and recycle of unconverted reactants, overall process conversion approaches 100%. This figure illustrates a typical ammonia synthesis unit where the reactor conversion limited by equilibrium is enhanced by recycle of the unconverted synthesis gas after waste heat recovery, chilling by ammonia refrigeration, and separation. Another example is production of propylene by dehydrogenation of propane. Shown in this figure is a propane dehydrogenation unit to produce propylene. The equilibrium conversion is 45%. Equilibrium conversion is influenced by increasing the temperature, but increased temperature has practical operational limitations such as formation of coke and reduction of catalyst activity. By separating the unreacted propane and recycling it to reactor, 100% conversion can be approached. The feed to the reactor consists of 0.45 ton of fresh propane and 0.55 ton of recycled propane, making a total of 1 ton of propane feed to the reactor. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.